Hello and welcome to section 4.8, where we look at some more conformational energy profiles, this time of butane. So we're going to start off just like how we started off our look into ethane and propane, and let's draw butane here in bond line structure. Now, here you can see that butane I'll just move this guy here. There we are. You can see that it has a hydrogen on this wedge here, a hydrogen on the dash here, but a carbon pointing up this time, CH3 group. And in the back, once again, hydrogen on the wedge, hydrogen on the dash, and another CH3 group in the back. And as we did before, if we want to look at that carbon, we set up our Newman projection by looking right down that carbon-carbon bond. There we are. And so our Newman projection looks a little like this. Oh, I should color one of these colors, not green, right? There we are. Cool. Okay. So the front hydrogen on a wedge is here. The front hydrogen on a dash is here. And that CH3 group is pointed straight up like this, right? Whereas in the back, we can start with that CH3 group there. It's pointed down, while the hydrogen on a dash is here on the right, and the hydrogen on the wedge is on the left. And so we can draw in a staggered conformation pretty easily, but hopefully after last lecture, you can see that if we start to turn this molecule now, the top or the bottom, we're going to start running into some big energy issues. And just as we did before for ethane and propane, we can actually map the energy changes associated with moving the top or bottom. So I say we focus on just moving the top and start, as we did before, by dealing with the staggered conformation first. So let's put our CH3 here. The H on a dash, the H on a wedge. And in staggered conformation, remember, we have no bad interactions here, right? I'm actually going to move some of these things. There we are. Okay, very cool. So now we could say our staggered conformation is here. Actually, why don't we move this one from the bottom here? I thought I wanted it there, but it turns out I don't. There we are. We're going to move them all around. Do a little shuffle. There we go. Okay, so let's say that we then twist 60 degrees to get an eclipsed conformation. So let's draw our back substituents first. Okay, and our front substituents now are going to be eclipsed. So now we have a hydrogen here, a CH3 here. Whoops, I have a bad habit of that. And another hydrogen here. Okay, so as we talked about before, we get 4 kilocals from this eclipsed interaction, or sorry, kilojoules, but we get 6 kilojoules. Is that right? Or is it 5? I forget. We get, how many? We get, 6 kilojoules per mole from each of these hydrogen CH3 eclipsed interactions. And that means that we are going to have a much higher energy for this eclipsed conformation. We'll put it here. There we are. This should be eclipsed. We'll call it eclipsed 1. All right. And we can draw a line going up there to it. All right. So that was our eclipsed conformation. But if we turn it 60 degrees again in the same clockwise manner, now we relieve some of that strain. Oh. There we go. By giving each of these now its own space, except for one little caveat. If you notice, the two CH3 groups are now next to each other. And this is a special situation that we call gauche with a G. Gauche means left in French. And here it means the situation where substituents, large ones like CH3 or larger, are immediately next to, left or right, another large substituent. But not in an eclipsed fashion. So this is my own little definition. Hopefully you find that helpful there. So gauche is like you see it here, where these two CH3 groups are right next to each other, but they are not eclipsed. But there's still an energy penalty associated with them being right next to each other, and that is an energy penalty of 3.8 kilojoules per mole. So that means we don't go right back down to the staggered energy that we had before, and instead we go a little higher here. We'll mark that G for gauche. And we can also go down just like before. Okay. Next, we have a situation where if we rotate another 60 degrees, hopefully now you see that there's going to be a big problem. And that big problem is that we're going to have two CH3 groups that are overlapping each other in an eclipsed manner. So if we draw that, it looks like this. Here's the back again. And here's the front once more. There we are. So now we have one eclipsed CH3-CH3 interaction and two eclipsed hydrogen-hydrogen interactions. So if you remember, each hydrogen-hydrogen eclipsed interaction gets 4 kilojoules for a total of 8. And the carbon-carbon eclipse interaction gets 11 kilojoules per mole. So that gives us a total of 19 kilojoules per mole, which is much larger than the 16 we got before. And if we were to draw this, just move this out of the way. I'll just redraw it over here. then it would be like up here. And we'll call this eclipsed 2. And as before, we can go up the energy landscape like this. Now, if you remember, by continuing to rotate this 60 degrees, we can find the next ghost state, because there are 2 degenerate ghost states, right? In one, oops. So here are the back substituents for each of the degenerate ghost states. But the front substituents look a little different, right? Because they're both free from any eclipsed interactions, but one has a CH3 on one side, and one has a CH3 on another side. So the gauche interaction is here and here on the other. Okay, these both have the same exact energy. You can see that clearly in your book on pages 154 and 155. Right. So then last, I'd like to talk a little bit about table 4.6 in your book. It's a pretty nice table, and it gives you an overview of all of these energetic considerations that we just talked about, the hydrogen-hydrogen eclipsed conformation and its energy cost, carbon hydrogen, CH3 hydrogen, the CH3-CH3 eclipse interaction, as well as the gauche interaction. And you see that there are differences there. They have differences in torsional strain or steric interaction. And again, torsional strain is that energy difference between a CH3 and an H eclipsed. There's no steric problem there. It's just a torsional issue due to that anti-bonding orbital overlap that we saw in 4.7. Whereas the steric interaction they're talking about here is the interaction between 2 molecules that are physically too large. The sterics are too much, and they repel each other away. So that's why you have a steric interaction there. And this has been section 4.8.